notes are about inverse variation. This might be a phrase that you've heard before, maybe in science class. We're going to talk about what it means and then later on just look at the mathematical side of what inverse variation can tell us with particular functions. So let's start off with an example. You've probably, hopefully, seen this relationship before. D equals R times T. That's distance equals rate times time. So if you know the rate at which you're driving and for how long you're driving, you know the distance that you've driven in that time. So that's the relationship between distance, rate, and time. Let's look at two scenarios. Scenario 1. Let's suppose distance is constant. Let's let distance equal 50 miles. In that case, our scenario is 50 equals rate times time. Let's think about this. We're driving 50 miles. I know we have to go 50 miles. And I'd like to know how are rate and time related. So let me think about what happens as rate increases. So we know we're going 50 miles. That's not changing. The faster we go, the less time it will take. As rate increases, time decreases. So if I'm going really fast, it's not going to take very long to go 50 miles. If I'm not going so fast, it'll take longer. That relationship is known as inverse variation. We can say that R varies inversely with T. If I wanted to create a graph of that scenario, let's say I'm talking about R and T, so let's say R is kind of on our x-axis and T is on our y-axis. As R is growing, T is shrinking. So our picture might look something like that. We're going to investigate more aspects of that graph, definitely in class, but there's a quick picture to show you what's going on. Think about another way I could write that equation. I could also solve for R to investigate. I know that R is equal to 50 over T. Now I can really see, oh yeah, as T is getting really big, 50 divided by a very large number is going to be a very small number. So the equation should also make sense. How about scenario 2? Now let's let rate be 40 miles per hour. Let's let our rate be constant. So in other words, D is equal to 40 T. So now I don't know my distance, but I know that no matter what I'm doing, we're driving 40 miles per hour. So let's think about what's happening, or a relationship between time and distance now. Instead of rate and time, let's think about distance and time. As time increases, well, now we're driving at the same rate for more time. You're going to go a further distance. D increases. So as time increases, D is also increasing. You're driving for the same rate, just for longer, so of course you're going more miles. That's known as direct variation. We can say D varies directly with T. And actually, if I asked you to graph D equals 40T, that's old news. That's just a linear graph. I'll do that one a little bit smaller here. If we have time now on the x-axis and D on the y-axis, your graph's going to look something like that. So with this relationship, D equals R times T, R varies inversely with T, and we can see that D varies directly with T. Of course, I could also think about, I don't know, R and D, or what other combinations we could do, but that's an example of inverse variation and direct variation. Let's kind of approach this from more of a mathematical standpoint. Let's kind of remove the context. Let's take a closer look at an equation that can represent inverse variation. If you remember from when we let distance be constant, we had R times T equals 50. In general, without a context, let's just use X and Y. We can say that X times Y is equal to K. If you like looking at your equations in terms, Y in terms of X, you could also rearrange these things and say Y equals K divided by X. These equations represent inverse variation, where k is known as our constant of variation. In our previous example, if x or r times t equals 50, 50 was our constant of variation. It took the place of k here. But I can say this as y varies inversely with x. Y varies inversely with x. Direct variation has an equation with the following structure. Y equals your constant of variation times x. Think about what the graph of that would look like. It would, of course, be linear with a y-intercept of 0. Y equals k times x. We would still call k our constant of variation, but this time we would say this as y varies directly with x. Is it possible for a variable to vary directly with one variable and at the same time inversely with another? Of course. How about this one? Y equals k times w over x. Sure, there's 3 variables in our equation, but that's okay. We have 3 kind of values, y, w, and x. K is still our constant of variation. In fact, let's pick a constant of variation. How about 7? Y equals 7w over x. 7's just our constant of variation, but I can say y varies directly with w and inversely with x. So you know relationships between variables. I don't know, a equals pi r squared, or PV equals nRT. Maybe you've heard of that one. And we can talk about the relationship between any 2 or more variables as varying directly or varying inversely. Let's end with one more example of this. Suppose A varies inversely with B and directly with C. When A is 6, B is 4, and C is 3. Find A in terms of B and C. Let's try to write out mathematically what is written here. Let's let K be our constant of variation. So A is going to vary inversely with B and directly with C. So we're going to have KC divided by B. Now I just have to solve for K using the given information. When A is 6, C is 3, and B is 4. We can't assume that K is 1. Notice when I wrote the first equation in green, I let the constant of variation kind of just sit there as K. K was kind of our placeholder, and now we're solving for it. The easiest mistake to make is to forget that there is a constant of variation. It's not just A equals C over B. We're multiplying by some number. Let's solve for K. I can multiply both sides by 4, and then divide by 3. So K equals 8. So our final expression for A would be, let's see, KC, so 8C over B. There we go. Have fun with the practice.